Welcome everyone to this quarter's last Zoom for Thought Talk. Finishing us out this year, we will have Ryan, and he's going to teach us how not to get tangled up while square dancing. Take it away, Ryan.
All right. Yep, that's exactly right. So I guess, yeah, thanks to Vaki and Sam and Mr. Thought for organizing and inviting me. Like Vaki said, today we're going to be talking about irrational tangles and something called this like square dance, which I'll describe now. All right, so consider like the following scenario. We've got four people standing on the floor, and they're all holding a strand of a rope. So there's a rope between the person in position A and the person in position B, and likewise between person in position C and position D. So note here that I'm not labeling the people with A, B, and C, D. Rather, I'm labeling the positions that they're standing in. Okay, and so the square dance is you're going to take some actions, and what are the actions? Um, so the person in position B and D can swap places. B's and when they do that, B's strand, so the person who's in position B, their strand goes over that of person in position D. So if they started out in this configuration, then they'd end up kind of looking like that. That would be the first action we could do. And then the second thing we could do is like the whole group rotates 90 degrees clockwise. So the person in position A goes to position B, B goes to D, D goes to C, C goes to A. And what would that do? That would take this to just this. Okay, so you might be able to imagine that if you just keep repeating these two actions over and over again in any order, alternating, the rope will get pretty tangled up. So we can twist and then we rotate and then we twist some more and the rope gets pretty tangled up. And so the game or the activity is kind of like, given some tangle, how do you get it untangled? I'm just looking at the chat. Okay. And so this is an activity that was like developed by Conway in the 1960s when he was looking at these mathematical objects called tangles. And he was studying tangles in order to like prove some pretty good results on the classification of knots, and in particular, like make it easier to like enumerate knots with small crossings, I think. Okay, so sorry, my iPad is like a little laggy here, but yeah. Yeah, so like here's an example of just like these people kind of going crazy, dancing around, twisting the rope up. And yeah, like I said, given such a tangle, is it possible to untangle it? And then one other restriction that we'll put is it possible to untangle it using only these actions of twist and rotate, right? So like up here, I don't know why it's laggy. This would be like the twist, and this would be like the rotate action. So the answer is yes. And this might be kind of surprising. Maybe it's kind of clear that we can undo all the actions by just doing them in reverse in the order that we did them, right? If I just like twisted, rotated, then I could just rotate back and untwist, but I can't do these unrotate and untwist operations. I need to just do these forward rotate and forward twist operations. Okay, so like I mentioned, this is an activity developed by Conway in order to like study knots. So maybe let's tie this a little bit more to topology. So we've got a couple definitions here, and I'm leaving out like a couple technicalities, but that's mostly because the page of definitions is mostly just to convince you that there's some real math going on here, and but we're not actually going to be using these definitions much. So in general, an entangle is an embedding of the disjoint union of a bunch of arcs, so like the intervals, into the three ball. That's the closed three ball such that the endpoints of all the arcs are mapped to the boundary copy of S2. And so all these points are getting mapped to the ball, or sorry, all these arcs are getting mapped to the ball, and the boundaries are getting mapped to the boundary, basically is what's going on. And so you can imagine that, all these strands are sitting inside of this ball, and they're all kind of tangled up, an entangle. So a rational tangle is a specific type of two tangle. So two tangle, we're just mapping two arcs into the ball. And it satisfies a property that once you put the arcs in there, there's a homeomorphism of the ball with the disk cross the interval. So it's a homeomorphism of pairs, which sends the two arcs to like a 2-point set cross the interval sitting inside of the disk cross the interval. So what would that look like? That would look like we've got some two tangle. It's crazy in there, but it's rational if we can provide a homeomorphism onto this guy so that the arcs fall onto these like vertical copies of the interval. Okay, and then we have that two rational tangles are considered isotopic if there exists a homeomorphism of the ball with itself, which sends the first tangle to the second tangle, so Q to Q prime. And also we require that this homeomorphism restricts to the identity map on the boundary copy of S2. So basically what's going on there is we've got this ball and we can swish around like liquid like on the inside, but the boundary is fixed. So in particular, the points where the two arcs are nailed down are fixed. Okay, so one thing we can do, just kind of simplify life a little bit, is we can consider rational tangles via their tangled diagrams. Let me see the chat. Yeah. And so what's the deal there? We've got some tangle. It could be crazy. We're going to project it to like this disk because we can kind of like assume without loss of generality that all the points are on the equator. And then when we do that projection, we're going to keep track of the over and under crossings. And so isotopy of rational tangles ends up being completely so tangle diagrams completely determine rational tangles. It turns out that you can isotope a rational tangle into like this general position where when you project, you only get like crossings of two strands over one another. And isotopy of rational tangles corresponds to tangle diagrams differing by a finite sequence of so-called Reidemeister moves. I'm not going to really talk about what those are here. They're pretty simple to describe. It's just basically if you have a knot diagram, you can like slide some crossings over other crossings, and you can kind of just undo a knot kind of as it's placed on the table in some ways which you'd obviously think of. But the reason I mention this is because it turns kind of this hard problem of like, some abstract topology into something like a little bit more combinatorial, something that we can kind of get our hands on. Okay. So here's like a cool result that I'm not going to prove. It turns out that every rational tangle can be obtained from this like trivial tangle or like the zero or like a trivial tangle by a finite sequence of these moves that our squared answers are doing. So rotations, so that's where we have some tangle, we'll call it Q, and this is kind of like how I'm going to abstractly represent a tangle diagram, and then I rotate it. And then the convention that we'll take is we're going to rotate clockwise. So you can see that this Q kind of got turned around a little bit. Okay, and then a twist is the other operation. And what does that involve? It involves taking the strand on the northeast and bringing it over the strand on the southeast and then connecting it back up to the points. So these are these two basic operations, and it turns out that every rational tangle is obtained from a finite sequence of these two basic operations. Okay, so like let's see some examples of what's going on here. So we already saw this kind of trivial tangle. That's like if we just do nothing. So that's kind of our starting point. If we take that and we rotate, this is what you end up with. And if we take the untangle, the trivial tangle, and then we perform one twist, we get this, like this strand crosses over this strand. We can get like the opposite crossing if we do a tangle and then a rotate. And then we can also get some more complicated stuff, as you can imagine. Here we do 3 twists, rotate, then 2 twists, a rotate, and then a twist. And the way that kind of looks like is we can kind of see that the 3 twists are all packaged up right here. And then we rotate it. So this is kind of running horizontally. This is kind of running vertically. We rotated, we did 2 twists, and then we rotated again and we did 1 final twist. Okay. It's worth noting that not every 2 tangle is a rational tangle. So in particular, here's some counterexamples. So the thing that we notice on the left here is that basically there's this strand which is just knotted with itself. It's like a overhand knot in there. And then this strand just like goes around it. Doesn't really matter. This is never going to be obtained by a sequence of rotations and twists. That's sort of intuitive. And also you can think about there's no homeomorphism from the 3 ball to like the disc cross the interval, which is going to straighten out this strand. So that's maybe also sort of intuitive. And this is like a little bit more of a tricky example, but the point here is that however I move these endpoints around on the sphere, there's no way to get this thing unknotted. And because rational tangles can kind of always be unknotted by, or they can always be obtained from the trivial tangle by a sequence of rotations and twists, this thing is not going to be a rational tangle. So not all 2 tangles are rational, but rational 2 tangles are pretty nice. And what we'd like to do is we'd like to classify all rational tangles somehow up to isotopy. So kind of like what's like maybe like an algebraic invariant, or is there something that like classifies rational tangles? The answer is yes. And this is where we have kind of like the big theorem that we're going to be digging into today. And it goes as follows. So there exists a bijection between the isotopy classes of rational tangles and the rational numbers. And that's what gives them the name rational tangles. And so there's a little caveat is that we actually have to include infinity. And infinity we can kind of think of as, sorry, everybody's favorite rational number, 1 over 0. What am I going to call this bijection? I'm going to say if I've got a rational tangle Q, then I associate a fraction to it. It's like called the fraction of Q, and I'm going to note that f of Q. Okay, and so something which I won't talk about too much now, but you can kind of see this is just like a glimpse into kind of how this fraction gets associated to this tangle. And it's via like a continued fraction representation. So if Q can be obtained from the unknot by this sequence of twists and rotations, and then maybe you can kind of think that I never have an exponent on my rotation because if I do 2 rotations, that really doesn't do anything to the tangle. We'll see that a little bit more later. But if I've got a tangle, a rational tangle, which can be obtained by this finite sequence of twists and rotations, and the fraction I associated to it is this continued fraction right here. So right here, I guess maybe I'll pause. Maybe I'll pause and see if anybody has like any questions so far.
Yeah. So one small one. What gets mapped to infinity? Like I'm sure it's implicit in what the formula just wrote down, but.
Yeah, like you're asking about the knot which gets mapped to infinity.
Yeah. Mm-hmm.
Yeah. So it ends up being this knot.
I see.
Yeah, so we're going to see that this knot kind of maps to 0, and this knot, or not tangle, maps to infinity.
Oh, and okay, again, also I think this might just be implicit in your formula, but like whenever we do a rotation, we're basically just like flipping the fraction over. Is that correct?
Yeah, Yeah, so we're gonna see that actually.
Okay, cool.
Yeah, so we're gonna see that actually. And then yeah, that's what's going on essentially in the formula. Is whenever there's like a rotation in between some twists, we're doing some sort of like reciprocal thing, negative reciprocal. So okay, so
just a quick question. Sorry.
What's that?
Very quick question. Is a two tangle like a braid on two things, on like two
So
strings?
it's actually not a braid.
It's not, okay.
And the reason is because so tangles, two tangles subsume like two braids. So every two braid is a two tangle, but you can find two tangles which are not two braids. So like let's go up to the example here. This is an example of a two tangle, a rational tangle, which is not a braid, which is not a two braid. And that's because braids, so these would all be braids, are actually, I don't know about that one. Yeah, I don't think that one. But like these would be braids, but this guy wouldn't.
Okay, I see.
It's because of this extra thing that we can do is we can
Mhm.
rotate. Cool.
I also have a question.
Yep.
I don't know if you were getting at this, but what happens when you rotate twice? Is that just, we're assuming that there's a t to the 0 or something?
Yeah. So I like purposefully like kind of wrote this a little, like I'm a little vague here. Actually I can even have like a rotate on the end of this. And then you'll get a similar formula. You'll just reciprocate again and like add a 0 in the front. But yeah, I don't know. It's just like a little bit messier. And what happens when we rotate twice? I'll talk about that in a little bit. Okay. So yeah, so what I wanted to say was I'm not going to prove this theorem today. There's kind of like a lot of material that goes into it. As far as the attribution for this theorem, so like a lot of I'm honestly like not entirely sure. Like a lot of sources like attribute this to Conway, but I also have seen some sources that say like Conway just like wrote this down and like didn't provide a proof of it, and Kaufman is also maybe like I've seen like proofs by like Kaufman. There's like a bunch of proofs of this fact actually, and some of them are actually like pretty elementary, but I think it's like still a bit just too much to get into all the details. So what I want to try and do is give you some sense of why rational tangles might be related to continued fractions, and why you'd think to even kind of assign this numerical invariant to a tangle anyway. Okay, so if you're kind of, if you're these like squared answers trying to figure out the theory of tangles, there's like a particularly like simple class of them, and it's all like the braids, right? So these are tangles that I can get without, sort of like these are tangles I can get without like rotating at all. And then these tangles are sort of similar, but their crossings are reversed from these guys. So all of these, it's kind of natural to associate some integers with them, and namely like an integer can kind of count the crossings up to sign. So this is like has 0 crossings, this has 1, this has 2, and we can see that each subsequent tangle can be obtained from the next with an action of t. So if I twist, I go from what I'm calling -2 to -1. If I twist again, that comes to 0, etc. Okay, and so like somehow this is telling us that we should, whatever number we want to assign to our tangles, we should think of t as doing like a +1. Right, so this is kind of like just a loose idea, but we should think of t as doing a +1. Okay, so what about rotations? So maybe this is like a little trickier. So maybe the first example that we can see is we can just take what we called 1. If we do a rotation, then we get what we were calling -1 because it just like reverses the crossing. And so you might think that a rotation sends a number to like minus a number. But this is like pretty clearly false because I mean, if we just take 0 and we do a rotate, then it's like definitely not like -0. And also, we can have like another example. So if we start with just our trivial tangle here, and we apply 2 twists, then we get this thing, which we've been calling 2. And now what happens when we rotate it? So we get some other rational tangle. And I have no idea what its number is, but let's just call it x, okay? So an observation we can make is that if we apply a twist to x, then we're getting sort of maybe what you might reasonably call minus x. And the reason is because the crossings have swapped. So this overcrossing became kind of like an undercrossing. And this guy became this guy. So at least for the story that we had up here, when we said that reversing crossings is somehow like a negative, then that tells us that that this should be like negative x for whatever x is here. Meanwhile, we did a twist in order to obtain this, and a twist should correspond to like a +1, right? So we can actually kind of just like set up, a simple equation here. If I take x and I twist it, that should be +1, but evidently it's doing a minus. And so this tells me that x is equal to -1/2. Okay, so this is like sort of weird. We were like jumping out of the integers all of a sudden. And this like is maybe an indication that that it's not like x to minus x that we're looking at, but it's maybe something like x goes to the negative reciprocal of x. Okay, so to make this all like a little bit more formal, we can talk about these actions of R and T acting on the set of isotopy classes of rational tangles. So like this is just a free group on 2 generators, and I'm going to have the generators act by rotations and twists. And this is a transitive action because of that result earlier that said that all rational tangles can be obtained from just our trivial tangle by finite sequence of rotations and twists. So so this is kind of like setting up a correspondence between words in this free group on 2 letters, and isotopy classes of rational tangles. So a question you can ask, are there any relations? What's like the kernel of this action? One thing which I'm not going to prove, this is JJ's question, what happens if you rotate twice? So you get something which looks like this, and it actually turns out that if Q is rational, then these two are actually isotopic. So this is something that doesn't hold in general. For example, if I take that tangle from earlier, where I just had one of the strands completely knotted, and I perform 2 rotations to that, that thing is not going to be isotopic to the original. So like acting on the set of all tangles, R kind of has order 4. That's pretty obvious because if we rotate 4 times, that's certainly just doing nothing. But on the set of rational tangles, it actually has order 2 on the isotopy classes of rational tangles. So that's telling us that R squared is the identity. Okay, and then there's this like trickier relation that we can also observe. Okay, oh, that was way too much. Sorry, this is like being a little laggy and I'm not totally sure why.
It seems to be a running problem with the math houses, issues with the tablets.
Yeah, true. I have bad problems, I guess, yeah. Okay. Okay, so yeah. So now we've got this like a little bit more involved relation. And what happened? What's the story here? We start with a tangle, Q, and we rotate, and we get something which looks like this. Basically, the Q, it's convenient that Q is like a not very symmetric letter, so we can see what's going on here. And then we do a twist, and we get this. Do another rotate, end up with this, another twist, another rotate, and another twist, and we end up with this thing. And now you can see that there's this strand going from this corner all the way under all of these strands up to this corner. So what we can think about is taking that strand under the whole diagram and up until we get like that. And then it's pretty clear that once this is once we see that this strand is the same as like this strand by a sequence of Reitermeister moves, we can just like twist the whole diagram back into its original position. And so this sequence RT, RT, RT is actually the identity. So this is RT cubed. Okay, and so it turns out, this is another thing which I'm not going to prove, but it turns out that these are sort of the only relations that I can get. These kind of like generate the kernel of this action. Retweet, yeah. Yeah, so basically, so then my action of the free group descends to the action of this thing. And also what we can see here is that all of a sudden we can understand what is the inverse of t, just in terms of, so like what's a negative twist in terms of positive twists and rotations. And then if you're a square dancer, you might be pretty hyped about this because you've got yourself in this big mess. As long as you can remember the sequences of R's and T's, now all of a sudden you could probably get untangled, go home for the night, because you know what T inverse is. You've got a formula. Okay, so now here's kind of a cool thing. Some of you might recognize this presentation as the group PSL2Z. So what is this group? I think this is called the modular group, and it's SL2Z modulo the subgroup generated by negative the identity. And so what is that? Just to be sure, that's the group of all invertible matrices with integer coefficients. Oh, I don't really know why we have that. With integer coefficients whose determinant is 1, and then again, we just mod out. And so it turns out that this group actually has the exact same presentation. It's generated by two guys, alpha and beta. Alpha has order 2 and alpha beta has order 3. Okay, so that's cool. What are the matrices for alpha and beta? These are the matrices. So alpha is this matrix 0, negative 1, 1, 0. And I can see that if I square it, I end up with -1 right here, and 0's in the other place. But we're modding out by +(-1), so that's the identity. And then beta is this matrix right here. It's 1, 1, 0, 1. Okay, cool. So what's next? Well, we have an action of this group, PSL2Z, on the Riemann sphere. And how does it act? It acts by Mobius transformations. And in particular, it acts on the subset of the Riemann sphere, which is all the rational numbers lying on the real axis, union our favorite rational number, infinity. So how does the action work? I take a matrix A, B, C, D, and I act on X by, I do AX plus B, and I divide by CX plus D. And so there's like some, I don't know, pretty cool, I think like number theory and stuff. I don't know any number theory, but there's some cool stuff going on here. People think about it acting on like the half plane, and I think that you get like modular forms or something from that. Yeah, like Wikipedia, if you want to check it out, it has like a nice visualization of this action. The +1 kind of just moves everything to the right one. So these lines go to these lines, and then the negative reciprocation, that ends up being what this guy does. Kind of flips the whole plane all crazy. Yeah, so that's what I have here. Kind of spoiled it, but all right. So if we identify this kind of rational tangle group, it's like the set of it's like all these actions that we can do on rational tangles with PSL2Z, then R, right, our rotation corresponds to this matrix. And we said earlier that was like X going to 1 minus X, And indeed, if we look at what happens if we plug in 0, minus 1, 1, 0, then this fraction becomes minus 1 over x. Okay, and then t, or twist, corresponds to this matrix. And this matrix, you can also pretty easily see from looking at this formula, corresponds to it acts on x by sending it to x plus 1. Okay, cool. So, so under this correspondence, it's kind of under this correspondence, we can view the orbit of this trivial tangle under the group of actions that we have on rational tangles. Right, we said that those corresponded with isotopic classes of rational tangles, and under this kind of isomorphism, that's corresponding to an orbit of the rational number 0 under the action of PSL2Z. And the orbit of 0 turns out to be all the rational numbers union infinity. That's something that we can actually see in just a little bit. And so, but here's kind of where it all comes together. What is this element of PSL2Z acting on 0? Well, it's the continued fraction. It's a continued fraction an minus 1 all the way down to a1. And here I'm kind of using, I've been writing down r's and t's, like from left to right, thinking about the left one acting first. But here this is kind of like more standard like function notation. This guy acts first, and then this, and then down to the end. All right, so this is like pretty solid. This is like a good indication, you know, this is kind of the reason that we're like seeing these continued fractions pop up. Okay.
Quick question.
Yeah.
So assuming all the basic facts about rational tangles, it seems like the main work of this theorem was really showing that the kernel is precisely the subgroup generated by. Okay, cool. Just making sure.
Yeah, absolutely.
Cool.
Yeah. Basically, you want to say that like every rational tangle can be represented in this like kind of canonical form of like a word in our free group, basically. And that's where like the topology comes in, and that's pretty much the meat of it.
Thanks.
Yep. Okay, and then maybe just like one more question that you might have is like why is the PSL2 action transitive on Q union in infinity? And this is pretty much so this is like, you know, the rational numbers is generated by like add 1 and take negative reciprocals. And this is pretty much, I think, like just the Euclidean algorithm. So if we have a rational number P naught over P1, if it's an integer, then we can take it back to 0 by just adding a bunch of integers. So if it's positive, you know, we'll just subtract them. If it's negative, we'll add them. And if it's not an integer, what can we do? Well, we can add integers until we're in this interval, -1 to 0. Right, that can always be done. And then we can hit it with a negative reciprocal. And then repeat. And why does that work? Well, if we start with just a fraction P over Q, we add until we get it into this interval. And then when it's in this interval, we can write it as minus R over Q, where R and Q are positive integers, and R is strictly less than Q. Okay, and then when I take the negative reciprocal, that flips the denominator up into the numerator. And so what we end up with is like this guy is larger than this guy. So our denominator shrunk. And if we started with a finite denominator and we keep shrinking the denominator, eventually the denominator is going to go to 1, at which point we have an integer. And then we can just subtract or add to get to 0. So that tells you that any rational number can be taken to 0. And so any rational number can be taken to any other rational number by this group PSL2, because it's generated by this +1 and negative reciprocate. Okay. So the last thing, so maybe any questions here?
I had a question.
Yeah.
So like suppose you take A1 as 6 and A2 is 1 and just A1 is 5. Do they give isotopic stuff?
So you want to look at a particular example?
Yeah, like 6 minus 1 and 5. There are two different representations of the same.
Oh, yeah. Yeah, 6 minus 1 over 5, did you say?
1 over 1. Like, can it be 1?
Can it be 1?
Yeah. So like 6 minus 1 over 1 and 5. There are two different representations.
Oh, yeah.
Like continued
Yeah.
fractions.
So, right. So you're interested in this like non-uniqueness of representation.
Yeah,
of continuous
yeah.
fractions. Yeah. Yeah. Good question. It turns out that any non-uniqueness of representation of continued fractions is wrapped up into isotopies of rational tangles.
That's nice.
So yeah, so it's just, it works out really cleanly. They're gonna satisfy the same relations.
Is that buried in the statement that the original description of that group generated by R and T, you gave us acts on isotopy classes? Like that's really what's going on. And
Yep,
then you have the statement about the group itself, the statement about the kernel of the group.
Yes.
Or the kernel of the representation. I guess those two statements together give you this, that if you have two different continued fractions, you have isotopic tangles.
Yep.
Cool.
Yeah. So I mean, you know, the free group is going to act on like isotopy classes, or sorry, of just like, you know, rational tangles. But if you want to get these relations, then you need to introduce isotopy. Yeah. Okay. Oh yeah. So okay. So the last thing that I want to mention is, you know, sort of like our square dancers. Once again, you know, they've been dancing all night. They're probably really tired, and they might have forgotten the sequence of moves that they did in order to get into this big mess. Is there hope for them still? Can they look at their knot and figure out a way to untangle themselves so that they can finally go home? And so one way that they could do that is actually via this thing called a coloring of a tangle. So what's a coloring? So how can we compute this fraction f of q given a tangle q just by looking at the tangle diagram? So we've got this definition, which is an integral coloring of a rational tangle. It assigns to each arc of the tangle diagram an integer, or a color, with the property that the colors at each crossing are an arithmetic progression. So what does that mean? That means whenever I've got a crossing like this, the difference between A and B, that's the same as the difference between B and C. So another way to say this is that B is like the average of A and C. So that's an integral coloring, and it turns out, so some like knots are like not integrally colorable. You need to like mod out. You need to like color them with integers mod n or something like that sometimes. But every rational tangle is integrally colorable. And so here's an example. So let's look at the tangle I get from applying a twist 3 times. I can start at any of the strands and then just kind of start assigning colors. And then at each crossing, I pick a new color so that this condition about the arithmetic progression holds. So I've got 0 coming in, I've got 1 going over, so I need to have 2 coming out. And then I've got 2 going like this. I've got, oh yeah, at this crossing is when I can deduce that this strand needs to be 3. And at this crossing is when I can deduce that this strand this arc needs to be colored 4. Okay, and so now what are we going to do? We're going to look at all of the arcs that are coming to each of these endpoints, which I've labeled A, B, C, and D. And I'm just going to call the colors also A, B, C, and D. And so one thing which we can notice when we just look at this tangle diagram is that the diagonal sums, A plus D and B plus C are actually the same. So this is another thing I'm not going to prove, but this ends up being the case for all rational tangles. And so using this fact, we can actually come up with a way to produce the fraction of a tangle given a coloring. So if our squared answers can color, they're not, then they might have a chance of going home. And so the proposition is that the continued fraction, like the fraction you get from a rational tangle, is given by this quantity b minus a divided by b minus d. So that's kind of crazy. And it's actually like not too hard to see either. So we could prove it by induction. So so the base case is like, our trivial tangle here. This has a coloring 1, 0. No need to worry about really what we color these things because there's no crossings. So there's no conditions to be satisfied. And then if I look at b over a, b minus a over b minus d, that's 0 over 1, which is 0, which is what I should expect. That's the fraction associated to this trivial tangle. Okay, cool. Now what happens if we start introducing rotations and twists? So suppose that I've got some rational tangle and its fraction is b minus a over b minus d. Okay. Oh, I want to show this. I want to show that this is what's going on. So let's see. If I start with this tangle and then I rotate, then I've got new colors at all of these edges. A prime is going to be, let's see, A prime is going to be equal to C, B prime is going to be equal to A, D prime is going to be equal to B, and C prime is going to be equal to D, because I rotated clockwise. And so now, if I look at what happens, if I go ahead and compute this like weird fraction that just seemed to pop out of nowhere, I get the right thing. So B prime over A over B prime minus A over B prime minus D, that's A minus C over A minus B, just using the fact that it's a 90-degree rotation. And I can rewrite that as B minus D over C minus D, using the fact that, that these diagonal sums are the same for rational tangles. And then that's B minus D over C minus D, which is minus 1 over what our fraction was for our original tangle.
So you're doing induction on the word length, is that right?
Yeah, exactly.
Okay, cool.
Yep. Yeah, so basically, yeah, just want to show that like if I act on a tangle by R, then the fraction changes how I would expect. Yeah. And so similar thing going on here. It's like slightly more complicated. When we twist, we need to like assign a new coloring. And so A prime and A, those can stay the same, but now we've got like another arc. So B prime, so like this arc previously was this arc. So this is like B, and then this arc was D. So that tells me that this arc needs to be 2B minus D. So that yeah, so that the average works out. Okay, and then D prime, right? That's just our strand B. Okay, so now if we go ahead and compute the fraction, what do I get? So B prime minus A over B prime minus D. This is again just using the definition or just using what we observed here. And then I split this up and I figure out that it's 1 plus f of q, which is again what I expect to happen to the fraction when I add to it. Okay, so this is great. These squared answers can like look at their knot, color it. That's a fun activity, and then untangle and go home in pairs, I guess. But yeah, I think that's all I want to say. So thanks.
All right, let's give a big thanks to our speaker. Well, that was a really fun talk to end the year on. Anyone got any questions?
Yeah, so small thing. So every real number can be represented by like an infinite continued fraction.
Yeah.
So can you consider like infinite tangles and like recover back like the real numbers?
Yeah. So here's the thing. When you consider infinite tangles, you have you don't have as nice of a correspondence between kind of like the like combinatorial aspects, like these like Reitermeister moves and stuff, and what you like actually expect like the isotopy type of the tangle to be. So there's like tangles that you can get which are like they're kind of like infinitely nested and they're all piling up and like tangling into a point. And it seems pretty clear that their isotopy type is just like the trivial tangle, but you can't actually like get there because you don't have like a finite sequence of Reitermeister moves and stuff. However, people have considered so-called like algebraic tangles. So I'm like a little, I didn't like look too much into this, but I think it's like some generalization where you can consider like actually like addition and multiplication of tangles, and then you can like take rational tangles and look at what happens if you add and multiply tangles, and that gives you rational tangles, or sorry, algebraic tangles, and those are like those are messier still. Describe like a wider class of knots.
Out of curiosity, the thing that is excluding those infinite tangles is the thing you hid from the definition. Is that like that the embedding is an embedding in the sense of smooth manifolds, not just topology? Is that right?
Yeah, well, and there's also like, so I had like a few technicalities. Like you want it to be like a proper embedding, and then I even think that there's like some more stuff you want going on. Like knots. Like I somehow like you don't even want to think about them as like just S1 mapping into space, but you want like a solid torus kind of mapping into space. Yeah, so you want like a little tubular neighborhood around your arc, which I think is corresponding to like a smooth embedding. Yeah.
Interesting. Cool.
Yeah.
Any other questions? Alrighty, let's give the speaker another round of thanks.